Some stories have a way of getting under your skin. You might first dismiss them as unbelievable tourist fables, only to discover later that they are entirely true. It is in that moment of realization that your mind begins to spin, grasping the profound strangeness of the world we inhabit. I am about to share one of these accounts with you, a tale about a single morning that altered our understanding of reality. I suggest you get a cup of strong tea, as you are going to need it. Our story begins on June 30th, 1908, deep within the Siberian taiga. Picture a vast, endless expanse of sparse birch forests, where the silence is so complete you can hear a distant woodpecker at its work. The air itself is crisp, carrying the scent of pine and morning dew as the 7 o'clock sun filters through the trees. It is a scene of perfect tranquility, a typical Siberian morning, indistinguishable from millions that came before it. Until, and the thought alone is chilling, the sky suddenly detonates. This was not the sound of thunder or a flash of lightning. It was a genuine explosion, as if a second sun had just been ignited directly overhead. Eyewitnesses would later struggle to describe what they saw, a fireball so luminous it outshone the sun itself. Just imagine that for a moment. If you have ever dared to glance at the sun, you know the searing pain that makes your eyes water in seconds. This light was reportedly even more intense, like a celestial searchlight being switched on. Yet, the brilliance of the fireball was only the prelude. This object blazed across the atmosphere, trailing smoke like an aircraft. Except, of course, airplanes were virtually non-existent in 1908. The Wright brothers had achieved their first flight just 5 years prior, and it had lasted only minutes. But here was something the size of a large building, slicing through the sky at a speed so incredible the human eye could not follow it, leaving only a fiery scar from one horizon to the other. Then came the most terrifying development. The object did not impact the ground. Instead, it exploded while still in the air, unleashing utter chaos. Can you conceive of a sound that carries for 800 kilometers? To put that in perspective, it would be like a detonation in Moscow being clearly audible to people in St. Petersburg. The flash from the explosion was so bright that individuals across Europe were able to read newspapers at midnight without any artificial light, mistaking the glow for the long summer twilight. Seconds after the flash, the true devastation arrived in the form of the shock wave. Envision an invisible wall of force moving at the speed of sound that simply flattened everything in its path. Trees were felled like giant dominoes, pushed over by the hand of a titan. They were not shattered but laid down, all pointing in the same direction, radiating outward from the blast's epicenter. A staggering 80 million trees were leveled, a number that is difficult to fully comprehend. The immediate witnesses to this event were gripped by disbelief and terror. Some were convinced that a war had started, unable to imagine any other source for such a powerful explosion. Others saw it as a sign of the apocalypse, a scene straight from the Book of Revelation. The local Evenki people, who had inhabited these lands for generations, believed that angry spirits were delivering punishment upon mankind. And frankly, considering what happened, their explanation might not have been so far from the mark. What is truly astounding is that for a long time, nobody beyond the immediate vicinity knew what had occurred. In 1908, the world lacked satellites, radar, and even passable roads into such a remote region, with the closest town being hundreds of kilometers away. An explosion more powerful than an atomic bomb took place, and the rest of the world only learned of it 20 years later. Today, every detail would be broadcast globally within 20 minutes. The greatest puzzle, however, was not what happened, but what did not. A blast of that magnitude should have carved a crater the size of a small city into the earth and scattered fragments of iron and stone everywhere. There should have been detectable radiation or other chemical anomalies left behind. Yet investigators found nothing. Absolutely nothing. It was as if something immense had exploded and then simply vanished, like a magician's trick. Imagine yourself as a detective arriving at a crime scene where there is no body, no weapon, and no physical evidence of any kind. Only widespread destruction and witnesses speaking of a fiery dragon. That is the very predicament scientists found themselves in when they finally reached the location. For over 115 years, the debate has continued about what, precisely, exploded over Siberia that morning. Whether an asteroid, a comet, or something far stranger, the fact remains that a colossal and powerful object entered our atmosphere and staged a cosmic display whose repercussions are still studied today. Now, I want to introduce you to a man who witnessed this cataclysm firsthand, and I assure you his testimony will forever change the way you look at the morning sky. His name was Semyon Semyonov, and he became an unwitting participant in one of the 20th century's most profound mysteries. I remember getting goosebumps when I first read his account. Picture an ordinary Siberian trader sitting on the porch of his home in the small settlement of Vanavara, enjoying his morning tea and contemplating the day ahead. Vanavara was so isolated that the nearest town was a week's journey away by reindeer, yet it was a community of hunters, traders, and the local Evenki with their herds. Semenov operated a small trading post there, a hub where people would come for supplies like salt and ammunition, or simply to catch up on news. So there he was, on the morning of June 30th, gazing out at the taiga, when the entire northern sky was suddenly illuminated by a blinding flash, like a gigantic camera bulb going off. Semenov later recounted to investigators how the sky seemed to tear in two, with a vast elevated fire erupting over the forest. You have to understand what he meant by split. It wasn't just a brightening, but a violent cleaving, as if a cosmic blade had slashed the heavens to reveal an inferno behind them. This blaze grew in size, its brilliance intensifying by the second. The light was so searing, Semyonov reported, that looking at it was more painful than staring directly into the sun. He then witnessed the fireball streak across the firmament, charting a course from north to east and leaving a smoky plume in its wake. The moment the fire appeared, an intolerable heat descended, making it impossible to remain outdoors. Consider the immense temperature required to create such conditions in Siberia in late June. Yet, the most terrifying part was still to come. After the fireball disappeared behind the trees, in the short time it takes to count 1, 2, 3, absolute chaos was unleashed. A concussive shockwave struck Semenov where he sat on his porch, tossing him several meters as if he were a feather. As he later described it, I was thrown from the porch. I fell and lost consciousness. A testament to a blast that could hurl a grown man through the air. When Semyonov finally regained consciousness after some time, he awoke to an unimaginable panorama of devastation. The forest itself seemed to groan and splinter as trees were felled with a sound like mountains collapsing. A deep, pervasive hum filled the air, a vibration so powerful you could feel it resonating in your bones. But what I find most astonishing about his account are the specific details he retained. This man, with no knowledge of physics, remembered every minor element. He described the air smelling of smoke and something sour, how all the windows in his house were blown out, and how the iron roof on his barn was twisted like it was paper. As his wife ran outside screaming that the world was ending, he noticed one more strange detail. After the noise subsided, an eerie, deathly silence fell over the forest. No birds sang, no leaves rustled, as if every living creature had been frozen in terror. For nearly 2 decades, Semyonov was afraid to speak about what he had witnessed. In 1908, in an isolated Siberian village, recounting tales of fire from the sky would likely have you dismissed as mad or bewitched. He maintained his silence until scientists finally arrived, which is when the story becomes truly compelling. Because they came expecting to hear folklore about malevolent spirits. Instead, they were presented with a precise, detailed testimony that perfectly corroborated data from observatories thousands of kilometers away. Semyonov correctly outlined the sequence: the initial flash, the fireball's trajectory, the explosion, and then the shockwave. A progression that perfectly matched the physical phenomenon. A man who had never studied science provided investigators with crucial information for understanding the Tunguska event. What impresses me most about his story, though, is how this ordinary man faced something utterly incredible and simply remained human. He didn't become a prophet or start a cult. He didn't fabricate tales of aliens. He just continued his life, trading and raising his children. And only when asked did he honestly describe what he saw. That was Semyonov, a witness to a cosmic catastrophe whose testimony became a key source of information on an event that still baffles science. But Semyonov was not the only one to see it. There were people living in the taiga who understood that land far better than any scientist, and they had a very different version of what occurred that morning. Now, I will tell you about a man who was convinced he knew the truth, an Evenki shaman named Ivan Petrov. To him, the events of June 30th, 1908 were not a mystery, but an inevitability. While European scientists looked for a crater, debris, and radiation, the expected aftermath of a meteorite impact, the local Evenki, Yakuts, and Russian Old Believers knew from the beginning it was something else. Ivan Petrov, the old shaman, simply said, "Why are you surprised? It was Ogdi who came." In Evenki mythology, Ogdi is a fire spirit that has no place on Earth, and Petrov claimed his grandfather had warned that one day Ogdi would descend to show humanity its power. And so it did, with lightning and thunder, leveling the forest before returning to the sky. Petrov also insisted the impact zone was a special place he called Arakti, meaning a location where the Earth is sick. Remarkably, he was right. Modern research has confirmed that strange anomalies persist at the epicenter. Plants exhibit accelerated growth, animals behave erratically, and compasses malfunction. The old shaman explained that the world is divided into 3 realms: the upper world of spirits, our middle world, and the lower world of the dead, and that sometimes the boundaries between them can leak, resulting in events like the taiga explosion. He claimed he could sense a restless energy at the site from far away, saying, "The Earth remembers the fire," and he absolutely refused to go there. Despite researchers' attempts to persuade him with money and gifts, he would not be moved. Ogdi was sleeping there, and now he's awake, he stated. Why wake him? This is where it becomes truly interesting, because this wild shaman, with no training in physics, describes certain aspects of the Tunguska phenomenon more accurately than some scientists with all their instruments. He correctly asserted that the blast occurred in the air, not on the ground, and that the fire dissolved in the sky before it ever reached the earth. He also said the air itself was changed by the explosion, a claim later verified by measurements showing shifts in the atmosphere's composition. Furthermore, Petrov mentioned that for days prior to the event, animals throughout the region had been acting strangely. Long before the cataclysm, the animals knew something was wrong. Reindeer grew agitated. Dogs began to howl. Birds vanished from the skies. And bears sought refuge far in the wilderness, all seemingly aware of the approaching danger. Modern science validates this intuition, confirming that animals possess senses capable of perceiving shifts in the magnetic field, infrasound, and electromagnetic fluctuations that often precede major disasters. Perhaps the most startling revelation came from a local man named Petrov, who insisted that such cosmic events were not unique, but occurred with a certain regularity. While not an annual occurrence, he recounted his great-great-grandfather's tale of witnessing a comparable, though less intense, fire in the sky. He even shared an older legend about an iron mountain that fell from the heavens and detonated mid-air. This testimony makes modern astronomers uneasy, because the unbelievable truth is that Petrov's account was accurate. Our planet is under constant bombardment from space, with thousands of minor meteorites burning up in our atmosphere daily, and dozens of larger ones arriving each month. Approximately every century, a genuinely significant impact event takes place, proving that Tunguska was not an anomaly, but a predictable part of a recurring cycle. Petrov passed away in 1932, long before science would officially validate his claims. Yet his narratives live on, prompting ethnographers to this day to explore Evenki folklore for clues about ancient cosmic disasters. Their research has been fruitful, revealing that the legends of these northern peoples are rich with accounts of falling stars, heavenly fires, and the sound of thunder without any storm clouds. Another fascinating detail Petrov shared was the belief that the site of the explosion had to be fed with offerings to placate the angered spirit of the place. Remarkably, the Evenki people continue this tradition today, visiting the location to leave gifts of coins, ribbons, and bread, whispering, "Ogdi, sleep peacefully. We remember you." There's a profound wisdom here, not necessarily spiritual but practical. This site demands to be remembered, studied, and preserved as a stark reminder that space is not a tranquil void, but a persistent source of danger. In his own way, Ivan Petrov understood the Tunguska explosion as the work of powers far beyond human comprehension. And he was entirely correct. While he named these powers spirits, and we call them physical laws, the fundamental truth remains the same. The Tunguska event demonstrated that we inhabit a universe where the unimaginable can become reality in an instant, and for which we must always be prepared. Let's now shift our focus to the sheer scale of this catastrophe, as the incident in the Siberian taiga was far more than a simple loud noise. It was an event of such immense power that had it occurred over a major city like Moscow, you and I would not be here to discuss it today. To truly grasp the power unleashed at Tunguska, it helps to make a comparison. Think about the atomic bomb, Little Boy, that was dropped on Hiroshima, which had a yield of about 15 kilotons. This is equivalent to 15,000 tons of TNT, a quantity of explosives so vast it would require an entire freight train to transport. Now, consider this. The Tunguska blast is estimated at 10 to 15 megatons. Since a megaton is 1,000 times more powerful than a kiloton, this means Tunguska was approximately 1,000 times stronger than the Hiroshima bomb. To visualize this in terms of TNT, you would need a train packed with explosives stretching all the way from Moscow to Yekaterinburg. But even these figures are abstract, so let's examine the real-world consequences of such force. A staggering 80 million trees were flattened in an instant, radiating outward from the blast's epicenter like a giant had scattered a box of matchsticks. The total area of devastation spanned 2,000 square kilometers, an expanse larger than the entire city of Moscow and its suburbs combined. What is perhaps most mind-boggling is that all this destruction originated from an explosion that occurred high in the atmosphere, at an altitude of roughly 8 kilometers. Picture a detonation at the same height of passenger jet cruises. Yet the resulting devastation on the ground was comparable to a steamroller the size of a small nation having plowed through the forest. Eyewitness accounts report truly unbelievable phenomena. People located within a 50-kilometer radius of the epicenter sustained burns from a flash of light that lasted merely a few seconds. To cause such an effect, scientists have calculated the fireball must have reached a temperature of around 10,000 degrees Celsius, which is significantly hotter than the sun's surface temperature of about 6,000 degrees. The resulting sound wave enters the realm of the truly fantastic. The detonation was audible from over 1,000 kilometers away. Residents of Irkutsk were convinced a nearby gunpowder warehouse had exploded, while people in Kansk mistook it for the start of an earthquake. Even in the village of Nizhny Ilimsk, 800 kilometers distant, the sheer force of the sound caused icons to fall from the walls. But the effects didn't stop there. The atmospheric shockwave actually circumnavigated the entire globe 2 times. Our planet was quite literally made to ring like a bell, with seismographs registering a magnitude 5 earthquake in Irkutsk and a magnitude 4 in Tashkent. This brings us to the most enigmatic aspect of the event. A blast of this size should have carved out a crater at least 100 meters deep and 2 kilometers across, and it should have scattered debris like iron, nickel, and other rare metals typical of meteorites. There should have been some trace, radioactivity, altered soil chemistry, anything. Yet there was absolutely nothing. The initial expeditions to the epicenter discovered only an ordinary Siberian swamp. No crater and no fragments were ever found, almost as if the explosion took place in another dimension, with only its shock wave bleeding through into our own. Even more bizarrely, at the very heart of the devastation, a cluster of trees was left standing, untouched. Remarkably, only the trees in the surrounding area were toppled. At the very epicenter of the blast, a peculiar formation known as the telegraph forest remained standing. Trees stripped bare of their branches and leaves, resembling a field of poles. This phenomenon directly contradicts conventional physics. Imagine setting off an explosion where the center is untouched, yet everything in a ring around it is completely annihilated. For a long time, scientists grappled with this apparent paradox, unable to explain how such a thing could be possible. Eventually, researchers understood that this was the definitive sign of an airburst, an explosion occurring high in the atmosphere. In such an event, the shock wave descends in the shape of a cone. Directly beneath the blast at the cone's center, the force is immense but pushes straight down, allowing tall objects like trees to remain upright. However, along the cone's outer edges, the wave strikes the ground at an angle, leveling everything in its path with incredible force. While this insight explained the pattern of the devastation, it failed to address the most pressing question of all. What happened to the object that caused it? Had it simply disintegrated, vanished into thin air, or perhaps shifted into another dimension? This is the point where the truly compelling theories emerge. The deeper scientists delved into the Tunguska event, the more questions they had, leading to hypotheses that ranged from plausible, like a detonating comet, to wildly speculative, such as antimatter annihilation, or even an encounter with a miniature black hole. But those theories would all come much later. First, someone needed to physically travel to the remote location to witness the aftermath firsthand. This is where our central figure makes his entrance. A legendary and obsessed researcher, a true scientific detective named Leonid Kulik. You should remember his name, as without him, our knowledge of Tunguska would be virtually non-existent. We'd only know that something exploded in a remote place at some point. Kulik single-handedly transformed a Siberian folktale into a formal scientific investigation, and he would ultimately pay a steep price for his dedication, which I will get to later. Picture the scene. The year is 1927, nearly 2 full decades after the explosion, and the scientific community is only just beginning to show interest. The reason for this long delay was a period of intense turmoil that included a revolution, a civil war, and widespread devastation, leaving no resources or attention for investigating meteorites. Kulik, however, was different. He had been captivated by meteorites since he was a child, collecting space rocks with the same fervor others reserved for stamps. He crisscrossed the country, hunting for impact sites and documenting witness accounts, all driven by the dream of discovering the largest meteorite in Russia's history. When Kulik first heard the tales emerging from Tunguska, his excitement was boundless. He became convinced that a colossal meteorite, possibly the size of a building, lay hidden deep within the Siberian taiga, a literal mountain of iron that had plummeted from the heavens. He envisioned the studies that would follow, the renown it would bring to Soviet science, and the incredible discoveries it could unlock. Driven by this vision, he quickly organized an expedition and journeyed into the wilderness. The trek to the site was an immense challenge in itself. It involved a train ride to Krasnoyarsk, a steamship voyage up the Yenisei River, a long segment on horseback through the dense taiga, and finally a grueling march on foot across treacherous swamps. The journey covered thousands of kilometers and took months to complete, all in pursuit of a single cosmic object. And then, after enduring all of that, they finally reached their destination. As Kulik stood on the periphery of the forest, he was met with a panorama of destruction that exceeded his wildest expectations. For kilometers in every direction, the trees were felled as if by a hurricane of unimaginable power. Tree trunks so thick you couldn't wrap your arms around them were snapped in half like mere twigs. This scene of utter devastation extended as far as his eyes could see, a testament to an event of monstrous proportions. At first, Kulik was ecstatic, certain he had discovered the impact site of the greatest meteorite fall in recorded history. All that was left to do was press on to the center, locate the crater, and claim the prize, a 1,000-ton mass of celestial iron. Yet, as he and his team drew closer to the epicenter, his confidence gave way to a growing sense of confusion. There was no crater to be found. Absolutely nothing. The area was just a silent expanse of bogs and sparse trees, enveloped in an eerie quiet where not even birds would sing. Kulik and his team spent weeks conducting a meticulous search, methodically surveying the area square by square for any sign of meteorite fragments. They excavated pits and carefully inspected every natural depression they could find, but their efforts yielded nothing. They didn't find a single gram of cosmic iron or any geological evidence of a crater, leaving no indication that a large meteorite had ever struck the ground. It was in that moment of failure that Kulik grasped he was facing an entirely new kind of phenomenon, something that defied all existing scientific knowledge, a meteorite that had exploded in mid-air. Could it have been a comet? The idea seemed plausible, but comets are primarily composed of ice, which shouldn't be capable of causing such widespread destruction. Puzzled but far from defeated, Kulik returned from his initial expedition realizing that the mystery required a more advanced approach. He understood the necessity of new expeditions, equipped with more precise instruments and modern research techniques, and he dedicated himself to organizing them, returning to the taiga time and again with new tools and strategies. During one of these later trips, he discovered several depressions in the swamps, and immediately concluded that these must be the craters left by fragments of the meteorite. He hired a crew, began the laborious process of pumping out the water, and started digging. After a month of exhausting work and moving tons of earth, the excavation revealed only ordinary thermokarst depressions, which are natural formations caused by thawing permafrost, and had no connection to a cosmic impact. Even after this major setback, Kulik refused to abandon his quest. He remained convinced that the meteorite was out there, and that he simply hadn't searched in the correct location yet. He considered new possibilities. Perhaps the object had buried itself deep within the earth, or maybe it had shattered into countless microscopic pieces. He even entertained the idea that it might be resting at the bottom of one of the nearby lakes. Kulik's last expedition took place in 1939. By then, he was over 50 years old and in poor health, but his determination to find the truth was as strong as ever. And what's remarkable is that he was on the cusp of a breakthrough. In his final reports from the field, Kulik noted that he was beginning to reconsider his core beliefs, speculating that perhaps there had been no solid object involved at all. Unfortunately, just as he was approaching this revolutionary idea, the Second World War began. Kulik joined the military effort, was taken prisoner, and ultimately died in a camp in 1942. He passed away without ever learning that his final, revised hypothesis was correct. The Tunguska object was indeed something far different from a conventional meteorite. Though Kulik dedicated 20 years of his life to this mystery and never found the physical evidence he sought, he accomplished something far more significant. He transformed a regional legend into one of the most compelling scientific problems of the century. Thanks to Leonid Kulik's work, we possess a vast amount of information about the Tunguska event. Yet the most crucial element remains elusive. Let's explore the central mystery of Tunguska, the one that has frustrated generations of scientists and still perplexes them today. Where is the crater? And what became of the object that unleashed such widespread destruction? You have to understand, when a large, dense object from space collides with Earth at cosmic velocities, physics dictates a predictable outcome: an impact, a crater, and debris. This is precisely what you see in Arizona, with the famous Barringer crater, the result of a meteorite strike 50,000 years ago. It's a massive hole in the ground, 1.5 kilometers in diameter, and 170 meters deep, a clear, logical, and beautiful scar on the landscape. But in Tunguska, all logic seems to break down. You have an explosion more powerful than 1,000 atomic bombs, yet there is no crater. You have an object the size of a small building, but there are no fragments. You have temperatures reaching tens of thousands of degrees, with no evidence of anything melting. How could this be possible? This very question became an obsession for Kulik. He excavated half the taiga in a desperate search for even the smallest impact site. He discovered several lakes and believed he had found his answer, concluding that the meteorite must have landed in the water to form these depressions. After pumping the water out and digging into the lake beds, he found absolutely nothing. They were just ordinary thermokarst lakes, formed naturally when permafrost melts and the ground subsides. The most ironic part is that Kulik came incredibly close to solving the mystery. In one of his final reports he wrote, verbatim, "Perhaps the meteorite completely vaporized upon impact with the atmosphere." He used the word vaporized, nearly grasping what occurred, but ran out of time to fully develop the idea. This is where modern science, with tools like computer modeling, satellite imagery, and high-precision instruments, steps in to complete the picture. And what do these modern methods reveal? It turns out there was a depression, just not the kind Kulik was looking for. At the very center of the devastation, there is a subtle indentation in the ground, not quite a crater, measuring about 300 meters across and only a meter deep. It's so faint that if you didn't know exactly what you were searching for, you would walk right past it. Kulik himself likely passed it hundreds of times without a second glance, because he was anticipating a chasm the size of a football stadium. The critical insight is that this indentation was not caused by a physical impact. Instead, it was formed by the sheer force of the shock wave. Try to imagine an aerial explosion so powerful that the resulting blast wave literally pressed down on the earth, as if a giant, invisible hand had pushed into the swampy ground and left its imprint. Modern analysis has also uncovered something fascinating in the soil. Microscopic spheres of silicates and magnetites. These are the telltale remnants of rock that has been superheated to several thousand degrees and then cooled in an instant. So, while there are no large iron chunks, traces of the cosmic visitor do exist in the form of this cosmic dust. Can you envision it? A colossal stone plummets into the atmosphere, incinerates from friction, and detonates several kilometers above the surface, transforming into a cloud of superheated gas and fine particles. The gas dissipates as it cools, while the dust settles over thousands of square kilometers, leaving only a fine layer across the landscape as evidence of the meteorite's existence. But this explanation raises another, more complex question. Why did it explode? Standard stony meteorites don't simply detonate in mid-air. They might fracture or crumble, but they don't explode with such cataclysmic force. This implies that the Tunguska object was either not a typical meteorite, or was something else entirely. This is the point where scientific theories diverge. Perhaps it wasn't a solid body but a loosely bound collection of fragments that disintegrated. Or maybe it contained volatile substances that vaporized upon heating, causing the explosion. Another theory suggests it was spinning so rapidly that centrifugal force ripped it apart. Each hypothesis explains some aspects of the event, but fails to account for others. A stony meteorite would have left large fragments. An iron meteorite wouldn't have produced such a dramatic explosion. An icy comet, on the other hand, lacks the density to generate an explosion of that magnitude. Then you have the puzzle of its trajectory. Eyewitnesses reported seeing the fireball travel from the southeast to the northwest. However, the pattern of fallen trees radiates outward from a central point, suggesting the explosion originated from a single location. If the object had struck the ground at an angle, the destruction would have formed an elongated elliptical shape. This confirms it didn't impact the ground, but exploded in the air, symmetrically and in all directions, just like a bomb. So what kind of force could have turned a cosmic rock into a mid-air bomb? Here is where the investigation gets truly interesting. Modern research indicates that these kinds of airbursts have happened many times throughout Earth's history, far more frequently than we once believed. Most occurred over oceans or uninhabited regions, so they went unobserved. The Tunguska event was unique because it happened at a time and place where people were present to document it. It seems we live under a constant barrage from space that we are mostly unaware of, as the atmosphere incinerates most intruders before they reach us. The enigma of the missing crater taught us a vital lesson. Cosmic disasters do not always happen the way we imagine them. Our planet's defensive systems operate in ways we are only just beginning to understand. The atmosphere isn't merely a layer of air, it is a powerful, active shield. While this shield is not infallible, it is remarkably effective. Now, let's turn to the most widely accepted theory for what happened at Tunguska, the one that has the backing of most scientists and, incidentally, sounds a lot like the plot of a disaster film. This brings us to theory number 1, the official explanation for the nightmare that unfolded in the Siberian taiga. Prepare yourself, because this is the tale of a cosmic kamikaze that appears to have sacrificed itself for what can only be described as a truly spectacular fireworks show. Imagine an asteroid. Imagine an object not from a Hollywood disaster film, but something more restrained, measuring about 30 meters across, akin to a 20-story building turned on its side. This celestial body had a mass of 1,150 tons, comparable to a large ship, and was composed of stone and iron. It journeyed from the asteroid belt located between Mars and Jupiter, traveling along its orbit for millions of years, until its path fatefully crossed with Earth's. On June 30th, 1908, this object collided with our atmosphere at a staggering velocity of 54,000 kilometers per hour. To put that into perspective, 54,000 kilometers per hour is 1.5 times the speed of a bullet. Picture a rock the size of a building, moving faster than any projectile you can imagine. Its entry into the atmosphere triggered a process similar to a spacecraft's re-entry, but on a scale of unimaginable speed and power. The air compressed in front of the asteroid so violently that its temperature soared to that of the sun's surface, about 6,000 degrees Celsius. At such extreme heat, any substance vaporizes into superheated plasma. The asteroid began to incandesce, shifting from red to yellow, and finally to a blinding white, effectively becoming a flying sun that seared a fiery streak across the sky. This is precisely what eyewitnesses reported seeing, not the rock itself, but the incandescent envelope of air surrounding it. But this is where the truly fascinating physics begins. Under such immense speed and heat, the asteroid didn't simply burn. It began to violently disintegrate. Its surface boiled away, shrouding the core in a cloud of superheated gas and dust that exerted immense pressure, much like a steam boiler. Eventually, The asteroid could no longer contain this force, and it detonated, instantaneously converting all its kinetic energy into a catastrophic explosion of heat and a powerful shock wave. This aerial blast, with a force equivalent to 10 to 15 megatons of TNT, occurred at an altitude of roughly 8 kilometers. This specific height was the critical point where the atmosphere became dense enough to exert terminal pressure on the failing asteroid. Any higher, and the air would have been too thin to stop it. Any lower, and it would have already fragmented. The explosion generated a fireball several kilometers wide, with temperatures at its core reaching tens of thousands of degrees. This fireball expanded at supersonic speeds, creating a shockwave that radiated in all directions, up into space and down toward the ground. Upon hitting the surface, the wave reflected back, generating a complex interference pattern. In certain areas, the waves amplified each other, while in others, they canceled out. This phenomenon explains why trees directly beneath the explosion remained standing, shielded in a zone of cancellation, while everything in the periphery, struck by the wave at an angle, was leveled. While this explanation appears coherent and accounts for most of the observed phenomena, there are lingering details that continue to perplex scientists. For instance, the sheer power of the explosion is difficult to explain. While asteroids often fragment in the atmosphere, they seldom detonate with such force. Such an event would demand a rare convergence of specific composition, structure, and velocity that is statistically improbable. Further inconsistencies arise from the object's trajectory and chemical signature. The asteroid entered the atmosphere from the southeast at a low angle, which should have created an elongated, oval-shaped area of destruction. Instead, the devastation was nearly circular, suggesting the explosion happened high enough for the shock wave to lose its directional memory. Moreover, while microscopic spheres of rare metals like iridium, osmium, and platinum, all hallmarks of asteroids, were found in the soil, their quantities were far too low for a 150,000-ton object. This leads to other hypotheses, such as the object being a pure stone meteorite, but that wouldn't have produced such a powerful explosion, as stony bodies typically just crumble into a large meteor shower. Another possibility is a rubble pile asteroid, a loose collection of fragments. However, such an object would have likely produced multiple explosions, yet witnesses reported seeing only a single, massive fireball. Ultimately, the more information researchers uncover, the more complex the puzzle becomes. This means that either the standard asteroid theory is incomplete, or the Tunguska object was something far more unusual. Before delving into more exotic explanations, however, it's worth considering how scientists managed to reconstruct these century-old events at all. With no satellites or surveillance cameras, they relied solely on human memory, and some of the witness accounts described things that were initially dismissed as pure fantasy. What is truly remarkable about the Tunguska incident is not just the explosion itself, but the sheer number of people who saw and heard it, and how widely the news traveled. We are not talking about a few dozen or even 100 witnesses. There were thousands of them, spread across a vast region. The scale was so immense that the initial reports from many of these individuals were simply not believed by authorities. To give you a final sense of the event's magnitude, consider this. The flash from the explosion was visible from up to 700 kilometers away. 700 kilometers is an enormous distance. It would be like a massive detonation occurring in Moscow, with people in St. Petersburg witnessing a brilliant flash illuminating their horizon. That is the kind of power we are trying to comprehend. The sound of the explosion traveled for up to 1,200 kilometers, and seismographs across the globe registered the resulting shock waves. Yet, the most astounding aspect was the aftermath in the sky. For several nights following June 30th, strange lights appeared over Europe. In cities like London, Paris, and Berlin, the glow was so intense that residents could read newspapers at midnight without any artificial light, easily making out the fine print. We now know that this was caused by immense quantities of dust and gas thrust into the upper atmosphere, which then reflected the sun's rays. At the time, however, many believed they were witnessing something supernatural, with newspapers reporting on white nights in July, and astronomers being baffled by unusual noctilucent clouds, while the public speculated about divine signs. The process of gathering eyewitness accounts in Russia stretched on for decades, and a fascinating pattern began to surface. You see, the narratives grew increasingly surreal the greater the distance from the epicenter. Those closest to the event simply reported thunder and a shaking earth. Yet, 100 kilometers out, people claimed to have seen a flying dragon. At 500 kilometers, the story became one of the heavens splitting open. And by 1,000 kilometers, witnesses were describing epic battles between angels in the clouds. Initially, scientists were quick to disregard these stories as the ramblings of superstitious peasants and hunters, likely mistaking something mundane like swamp gas for a celestial event. However, a startling truth emerged when they eventually cross-referenced these accounts with instrument readings. The so-called uneducated witnesses had often captured the physical phenomena with greater precision than many trained observers. Consider the testimony of a reindeer herder named Lyul Utman. He was roused from sleep by a tremendous noise and, upon rushing outside his tent, saw a round object hurtling through the sky with a visible head and a multi-hued tail. The head glowing red, the tail a vivid blue. He claimed it took up more than half the sky, a statement that researchers dismissed for years as pure fantasy, since no meteorite could appear so large. But they later understood he was perfectly describing the object's atmospheric trail of ionized gas, which would indeed have filled a massive portion of his field of view from that close proximity. Another compelling account comes from a merchant named Brukhanov, who was 400 kilometers away in the town of Kirinsk. His diary entry noted an incredibly intense glow in the northwest sky at 4 in the morning, followed 10 minutes later by sounds resembling cannon blasts that shook his home and rattled the windows. This was puzzling, because the actual explosion happened at 7:14. Investigators first assumed the merchant had simply mistaken the time, but it turned out Brukhanov hadn't witnessed the explosion itself, but rather its lingering optical effects in the upper atmosphere. When you calculate the travel time for sound over 400 kilometers at 340 meters per second, it comes out to almost exactly 10 minutes. Incredibly, the merchant's personal record proved to be more accurate than many scientific instruments of that era. The most crucial evidence, however, came from people living in the settlements nearest to the impact zone. From Vanavara, just 60 kilometers away, to Kezhma at 200 kilometers, and Nizhny Ilimsk at 400, the reports were strikingly consistent. A blazing sphere tore through the sky, followed by a brilliant flash and then a powerful shockwave. In Kezhma, a priest named Father Kulesh wrote that as he sat on his porch, the heavens seemed to rip apart in a torrent of fire so blinding he had to shield his eyes. Simultaneously, he was struck by a wave of heat so fierce it felt like his shirt was igniting, leaving him with light burns despite being 200 kilometers from the event. Modern analysis confirms just how extreme the flash must have been, calculating the fireball's luminosity at the moment of detonation to be on par with the sun itself, which explains why looking at it was so painful. Agrafena Kostuzova, a resident of the nearby settlement of Vanavara, gave a chilling account of her experience. She recalled sitting on her porch, knitting, when the sky abruptly tore open all the way to the ground in a burst of flame, causing immense panic. Her description of the sky splitting open down to the earth is a remarkably poetic yet accurate metaphor for what people saw. A towering pillar of fire, stretching from the horizon up to the sky's zenith, just before it detonated in a blinding explosion. For a long time, the stories of the indigenous Evenki people were dismissed as mere superstition. This was a grave error, as their deep familiarity with the taiga meant they could distinguish every normal sound and natural occurrence. When they described the event as something not of this world, their words carried significant weight. A hunter named Ivan Mchedlov recalled being asleep when his entire hut was lifted into the air and thrown aside. As he scrambled out from the wreckage, he saw that his roof was gone and the surrounding forest had been completely leveled. He also noted that clouds then gathered and a hailstorm began. His description of his hut flying away perfectly captures the force of the shockwave, while the hail was a direct result of water vapor condensing in the violently disturbed atmosphere. In his own way, the Evenki hunter detailed the physical processes more accurately than some academics of his time. Ultimately, it was these personal accounts that enabled scientists to piece together a precise timeline of what happened on June 30th, 1908. They were able to determine the object's flight path, the exact time and height of its explosion, and how the shockwave spread. Without these human stories, the Tunguska event might still be an unsolved enigma. And perhaps the most significant takeaway is this. Despite their vastly different backgrounds, from reindeer herders to priests, every single person was witnessing the same fundamental event. Their descriptions were all consistent in their core elements, varying only in the finer details. The fact that this event occurred and was as astonishing as witnesses reported is beyond doubt. However, to grasp why a celestial rock would detonate with such incredible power, you must first appreciate the workings of our atmosphere and how it can paradoxically become a weapon against cosmic threats. We are so accustomed to the air we breathe that we seldom consider its remarkable nature. Yet this gaseous shield is far more than an envelope around our planet. It is a dynamic, defensive barrier that protects you daily from extraterrestrial bombardment, with the Tunguska event serving as a prime illustration of its power. To put this in perspective, consider that every single day, roughly 100 tons of material from space plunges into Earth's atmosphere, a mass equivalent to a medium-sized passenger jet. This constant shower consists of meteoroids, fragments of asteroids, and cosmic dust, raining down on our world ceaselessly. So why are you not constantly ducking for cover under a helmet? The answer is simple. Our atmosphere literally devours these invaders before they can ever reach you. When a space object breaches the upper atmosphere at speeds of tens of kilometers per second, a fierce battle ignites between the intruder's kinetic energy and the force of air resistance. Initially, the encounter seems benign as the object enters the thermosphere at an altitude of about 100 kilometers. The air there is so rarefied that astronauts pass through it without sensation. But for a body traveling at cosmic velocities, even those few molecules present a significant hurdle. Each collision with an air molecule transfers a minuscule amount of energy to the object, which might not sound like much. But with billions of these impacts happening every second, that energy accumulates with astonishing speed, causing the object's surface to heat up and initiating a powerful chain reaction. This escalating heat intensifies the interaction with the surrounding air, creating a feedback loop of destruction. As the surface grows hotter, air molecules begin to cling to it, forging a dense shroud of compressed gas that dramatically increases drag. This, in turn, causes the object to heat even more rapidly, transforming what was once a simple rock into a searing fireball of superheated plasma. With temperatures soaring to thousands of degrees and pressure building to hundreds of atmospheres, the invader is subjected to conditions that are impossible to withstand. Under such extreme stress, an ordinary stone melts and vaporizes, much like butter on a hot skillet. For smaller intruders, perhaps the size of a cobblestone, this process is final. They are completely incinerated, leaving only a beautiful streak across the sky we call a meteor. A fleeting flash that prompts a wish as the object dissolves into harmless, superheated gas. Larger bodies, however, those the size of a car or even a small house, are not defeated so easily, as their greater mass gives them a crucial advantage. While the object's exterior layers are melting and vaporizing away, its core remains comparatively cool and solid, allowing it to continue its descent while shedding mass but maintaining its incredible speed. It is here that the nature of our atmosphere becomes critical, as its density is not uniform. The air at sea level is 1,000 times denser than it is just 10 kilometers up, meaning resistance doesn't build smoothly but increases in sudden dramatic jolts as the object plunges deeper. Imagine the object streaking through the thin upper air, slowly heating and eroding, only to slam into the dense lower layers of the atmosphere. The resistance skyrockets, and the structural stress on the already weakened body becomes overwhelming, leading to a cataclysmic thermal explosion. In an instant, the remaining mass converts into superheated gas, transforming its immense kinetic energy into a devastating thermal blast, producing an effect similar to a thermonuclear detonation, but driven by entirely different physics. According to the consensus among scientists, this is precisely what befell the Tunguska object. It tore through the upper atmosphere, gradually breaking apart and superheating until it reached an altitude of 8 kilometers. At that point, the air was dense enough to exert a pressure it could no longer endure, causing it to violently explode. That specific altitude is no mere coincidence. For an asteroid of Tunguska's estimated size and mass, 8 kilometers represents a critical tipping point where conditions are perfect for a maximum yield airburst. The genius of this planetary defense is its inherent ability to scale its response to the level of threat. The smallest debris is safely incinerated at high altitudes, while medium-sized objects detonate far above the ground, producing spectacular light shows without causing any damage. It is only the truly colossal invaders, those spanning kilometers in diameter, that possess the mass and integrity to punch through this atmospheric shield and strike the surface. Yet this system is not infallible. On rare occasions, an object might be unusually dense, enter at a precarious angle, or possess a strange composition, leading to a Tunguska-like event. In these cases, the atmospheric defense mechanism activates, but produces a monstrous side effect, an airburst of unimaginable power. This creates a strange paradox where the very system that shielded us from a direct impact was also responsible for a near catastrophe of a different kind. The implications of this are chilling. Had the Tunguska object detonated over a major city like St. Petersburg or Moscow instead of the remote taiga, the consequences would have been unthinkable. What I find most unsettling is our continued inability to accurately forecast how any given asteroid will react upon entering our atmosphere. We have too many variables and unknowns to predict whether it will hit the ground or explode in the air, let alone at what altitude or with what force. The atmosphere, therefore, is a magnificent but deceptive guardian, creating a powerful illusion of safety that can be shattered by unpredictable and violent events. The Tunguska incident serves as a stark reminder that our planetary protection is not absolute, and that the cosmos can always find new ways to deliver shocking surprises. However, the asteroid theory is not the only explanation for what transpired in the Siberian wilderness. Another hypothesis, involving icy assassins from the outer solar system, may better account for some of the event's more bizarre details. And you know, this cometary explanation has some distinct merits. A comet, after all, isn't merely a piece of flying ice. It's more like a colossal, dirty snowball, often the size of a mountain, that rockets through the void at bullet-like velocities. Picture a comet's nucleus, several kilometers across, forged from a mixture of water ice, frozen gases like methane, ammonia, and carbon dioxide, and a smattering of cosmic dust, all compressed into a single, massive, frozen body. On its own, it might seem innocuous, just a giant snowball adrift in space. What harm could it possibly do? But consider what unfolds when this object plummets into Earth's atmosphere at tens of kilometers per second. The ice doesn't simply melt. It transitions directly into vapor, completely bypassing the liquid stage. This explosive process, known as sublimation, causes a single cubic meter of ice to expand into roughly 1,000 cubic meters of water vapor, an incredible 1,000-fold increase in volume. Now, project that effect across millions of cubic meters of ice detonating simultaneously, and you get an explosion with the force of a nuclear weapon. What's truly compelling is that such a blast would leave behind almost no physical evidence. The ice vaporizes, the dust scatters throughout the atmosphere, and the frozen gases simply dissipate. You're left with no crater and no fragments, only the haunting signature of the explosion recorded in the miles of flattened forest, precisely the scene discovered at Tunguska. This hypothesis was championed by Soviet astronomer Igor Ostapovich, who analyzed the object's path and found it inconsistent with a standard asteroid orbit, suggesting instead a highly elongated, comet-like trajectory. The timing, late June, also aligns perfectly with the peak activity of several known comet streams, and witnesses even described the fireball as having a long, luminous tail, a feature characteristic of comets, not asteroids. There is, however, a significant challenge to this idea. If a complete cometary nucleus, kilometers in diameter, had struck the atmosphere, the resulting explosion would have been far more powerful. Not 10 megatons, but closer to 100 or more. A blast of that magnitude would have obliterated not just the local taiga, but a vast portion of Siberia. Consequently, astronomers propose that it wasn't an entire comet that entered the atmosphere, but rather a smaller fragment. Comets are known to fracture as they near the Sun, either from gravitational stress or the pressure of outgassing, creating a swarm of debris along the same orbital path. A piece roughly 100 meters across, weighing several million tons, would possess enough mass to breach the upper atmosphere, yet be porous enough to detonate in mid-air before ever striking the ground. This fragment theory elegantly resolves certain anomalies that the asteroid hypothesis struggles to explain. For instance, The blast pattern at Tunguska was remarkably symmetrical. A fragmenting rocky asteroid would scatter unevenly, but an icy cometary body would vaporize uniformly, generating a symmetrical shockwave. Furthermore, chemical analysis of the site revealed elevated levels of rare elements and organic compounds typically associated with comets, not the metallic elements characteristic of asteroids. The cometary hypothesis also accounts for the strange atmospheric phenomena reported for several days following the event. The immense quantity of water vapor and fine ice particles thrust into the upper atmosphere could have formed noctilucent clouds in the stratosphere. These high-altitude clouds would have reflected sunlight long after sunset, which explains why people across Europe reported being able to read newspapers by the eerie glow of the night sky. Of course, the comet theory isn't without its own problems, the most significant being the question of its origin. In late June, most known comets are located far from Earth's orbit. One possibility is that it was a previously unobserved comet, perhaps making its first journey into the inner solar system from the distant Oort cloud. Another is that it was a fragment that had calved off a known comet years before, following a slightly different trajectory. An intriguing candidate is Comet Encke, which has a short orbital period of just over 3 years and makes regular close passes to Earth. While calculations confirm the main nucleus of Comet Encke didn't collide with our planet in 1908, it's conceivable that a stray fragment from its debris stream did. In essence, the cometary theory presents a very persuasive case. It effectively explains the mid-air explosion, the absence of a crater, the symmetrical destruction, and the peculiar chemical traces left behind. Its primary weakness is the lack of any direct observation of a comet approaching Earth on that day. But as the saying goes, absence of evidence is not evidence of absence. The object might have been too faint for the limited astronomical instruments of 1908, or perhaps records of its sighting were lost. Comets are notoriously unpredictable, capable of appearing from nowhere and vanishing just as quickly. For now, the cometary theory remains a leading explanation for the Tunguska event, a strong rival to the asteroid hypothesis. Both have their strengths and weaknesses, and the truth, as it so often does, may lie somewhere in between, or in a direction we have yet to consider. You see, in 1945, an event occurred that forced scientists to re-examine the Tunguska mystery through an entirely new lens. On August 6th of that year, Hiroshima experienced a blinding flash, a colossal fireball, and a shockwave that caused devastation for miles in every direction. For the first time, the world had seen the terrifying power of an atomic weapon. It was then that someone recalled that strikingly similar effects had been documented in the remote Siberian taiga 37 years earlier. A flash of light more brilliant than the sun, just as was reported in Hiroshima. A fireball stretching several kilometers across the sky, another parallel to Hiroshima. A shockwave that flattened everything in its path for tens of kilometers, precisely like Hiroshima. The temperatures reached tens of thousands of degrees, again, just like Hiroshima. The area of destruction was comparable to that of the atomic bomb, only it was dozens of times more extensive. This led some particularly imaginative researchers to a startling conclusion. What if the Tunguska explosion was, in fact, nuclear in nature? Could someone have possessed the secrets of atomic energy as far back as 1908, and was this the world's first test of a nuclear device? The notion is undeniably fantastic, but you have to consider that all the observed phenomena of the Tunguska event align with a nuclear blast. The intense light, the penetrating radiation, the electromagnetic pulse, and radioactive contamination. But wait, was there actual radioactive contamination? This is where the story takes a fascinating turn. When Soviet physicists explored the Tunguska region with dosimeters in the 1950s, they did find heightened levels of radiation. While not critically dangerous, the readings were noticeably higher than the natural background level. Furthermore, an analysis of the growth rings of trees that survived the 1908 event revealed isotopes that are characteristic of nuclear reactions. The problem, of course, is figuring out how nuclear weaponry could have possibly existed in 1908, a mere 12 years after radioactivity was first discovered, and long before nuclear fission was achieved in 1939. This is the point where conspiracy theorists enter the picture, each offering a theory more outlandish than the last. Could it have been a clandestine weapon developed by Tsarist Russia, or perhaps an experiment by Nikola Tesla involving wireless energy transmission that went catastrophically wrong? Maybe it was extraterrestrials testing their own advanced weapons. Among the more plausible of these fringe ideas is the concept of a natural nuclear explosion, suggesting that critical masses of uranium or plutonium can occasionally form in the Earth's crust and trigger a spontaneous chain reaction. You might remember that a natural nuclear reactor did operate 2 billion years ago in Oklo, Gabon. But that was an underground phenomenon, whereas the Tunguska event was an aerial explosion. Another hypothesis involves a collision with antimatter. The annihilation that occurs when matter meets antimatter releases a tremendous amount of energy, far exceeding a nuclear reaction. A few kilograms of antimatter could create a megaton-scale blast, leaving behind no radioactive fallout, only pure energy. But that raises another question. Where would a piece of antimatter even come from in our corner of the galaxy? It is incredibly volatile and is destroyed the instant it makes contact with ordinary matter. For it to have reached our planet, it would have needed to be contained and isolated somehow. This is where the imaginations of theorists truly took flight. Was it an alien starship powered by an antimatter engine that malfunctioned and exploded upon entering our atmosphere? Or did aliens detonate their vessel intentionally as a demonstration of their technological superiority? The most daring theories went even further, postulating the involvement of black holes, wormholes, parallel universes, or even a rift in space-time itself. Each new explanation seemed more bizarre than the one before, often accounting for some facts while conveniently disregarding others. But here is the ironic twist. The radiation in the Tunguska region was eventually identified as entirely ordinary. It originated not from a nuclear blast, but from natural sources, as the soil there contains a high concentration of radioactive minerals. The isotopes discovered in the trees were actually the result of atmospheric nuclear tests conducted by global powers in the 1950s and 1960s. It became clear that Tunguska's supposed radioactive signature was an artifact of much later events, not proof of the explosion's nuclear origin. And as you might expect, investigators found no evidence of alien spacecraft, antimatter, or black holes at the site. Nevertheless, the conspiracy theories have proven remarkably durable. Even now you can find articles online asserting that Tunguska was the outcome of secret experiments, alien interference, or even time travel. People are drawn to these ideas because, frankly, they are more exciting than the mundane reality of an asteroid or comet impact. And, to a certain degree, you can understand the appeal. Tunguska is a genuinely puzzling event, filled with too many strange coincidences and oddities. an explosion of just the right power, at the perfect altitude, in a uniquely remote location. It almost feels as though the entire event was staged. However, science operates on evidence, not coincidences, and at present, all the available evidence points toward a natural cause for the Tunguska event, whether it was an asteroid, a comet, or some other object from space. What's crucial is that it was something physical and explainable by the laws of physics. That said, even the most fantastical theories offer at least one benefit. They compel scientists to think beyond conventional boundaries, to explore unconventional lines of reasoning, and to entertain even the most exotic possibilities. It is truly fascinating to see how the conspiracy theories surrounding Tunguska have evolved in lockstep with our own scientific and technological progress. These stories about UFOs and antimatter are not just random flights of fancy. They reflect the shifting boundaries of what we consider possible. In the 1920s, as humanity was just beginning to dream of space travel, the most radical theory was of a crashed celestial ship. Then, in the 1940s, following the invention of atomic weapons, hypotheses about a nuclear blast came to the forefront. By the 1950s, with the space age dawning, theories involving aliens became immensely popular. It seems that with every new breakthrough in science, an attempt was made to connect it to the enigma of Tunguska. Was antimatter discovered? Then surely an antimatter engine must have detonated above the taiga. Were black holes theorized? It must have been a microscopic black hole passing through the planet. Was string theory developed? The only explanation could be a tear in the very fabric of space-time itself. Of all the unconventional explanations, the UFO hypothesis is undoubtedly the most well-known, a concept heavily championed by the writer Alexander Kazantsev back in the 1940s. In his scenario, an extraterrestrial vessel met its end over the Siberian wilderness. He argued that the blast happened in the atmosphere rather than on impact because the alien crew deliberately triggered a self-destruct sequence to keep their advanced technology out of human hands. Kazantsev wasn't merely a science fiction author. He was also an engineer who calculated that only a matter-antimatter annihilation could generate an explosion of such immense power. But what could have been the source of antimatter in 1908? The logical answer, in his view, was an alien starship. It's a compelling and internally consistent narrative, yet one that remains entirely without proof, as no fragments of alien tech or traces of annihilation radiation were ever discovered in the Tunguska area. Despite the complete absence of evidence, people were convinced by this idea then, and a great number still are today. This opened the door for even more imaginative theories to surface. Perhaps time travelers from our future were conducting an experiment that went catastrophically wrong. Or maybe parallel universes collided, with the explosion marking their point of intersection. Each new hypothesis tried to solve Tunguska's central puzzle. How could such a massive blast occur without leaving any physical debris? Because conventional physics couldn't account for this effect, many reasoned that the cause had to be something truly extraordinary. This line of thinking even implicated the famed inventor Nikola Tesla. One popular theory suggests he was responsible, having accidentally aimed a powerful beam of energy into Siberia while testing his wireless power transmission system. This idea is loosely based on Tesla's real-life experiments and diary entries mentioning attempts to contact Robert Peary's polar expedition in 1908. However, even if Tesla possessed such a device, a careful analysis shows it couldn't have generated nearly enough energy to cause a cataclysm of that scale. The most outlandish explanation of all comes from Russian researcher Albert Portnov, who proposed that the Tunguska event was a consequence of time travel experiments in the future. According to him, 21st century scientists created a time machine that malfunctioned, sending the energy of an explosion back to the year 1908. He supports this claim by citing supposed chronal anomalies in the region, disturbances in the flow of time, where clocks behave erratically, people age slower, and plants grow with unusual speed. Naturally, no scientific validation for these claims exists, but that has hardly dampened enthusiasm for the idea. And what I find most fascinating is how these fringe theories can sometimes push serious scientists toward considering truly unconventional possibilities, like a collision with dark matter or an encounter with magnetic monopoles. Think about cosmic strings, for instance, hypothetical one-dimensional objects left over from the Big Bang. Or consider dark matter, which constitutes the majority of our universe yet remains undetectable to us. What if clumps of this mysterious substance occasionally collide with regular matter, creating bizarre effects like explosions with no discernible cause? Another possibility involves magnetic monopoles, theoretical particles with just a single magnetic pole that have never been found. If such a particle, accelerated to near the speed of light, were to strike our planet, the resulting energy release could easily be powerful enough to account for an explosion of any size. Cosmic strings are another captivating concept. These theoretical filaments are thinner than an atom but so dense that a single centimeter would weigh billions of tons. If one were to pass through Earth's atmosphere, the outcome could look remarkably similar to the Tunguska event. Of course, all of these ideas are purely hypothetical at this stage, but this is the very essence of scientific advancement. It often begins with a seemingly wild notion, which then evolves into a mathematical model, and ultimately faces experimental testing. It's entirely possible that 100 years from now, the Tunguska mystery will be solved by a branch of physics we can't even conceive of today. For the time being, we are left to consider asteroids and comets as the most likely culprits. This explanation might feel less exciting, but it is scientifically sound, a remarkable achievement for an event that happened over a century ago in a remote wilderness without any photographic records. But our world has transformed since then. We now have satellites, radar systems, and incredibly sensitive instruments that allow us to study a similar event in real time and with extraordinary detail. You would think that in the 21st century, an era of satellites, supercomputers, and artificial intelligence, solving a century-old mystery would be a simple task. We could have neural networks sift through the data, and quantum computers simulate all possible outcomes to reveal the truth. However, the reality is far more complex. Modern cosmic investigators face the same challenge that Leonid Kulik did a century ago. The more information we collect, the more questions seem to arise. Each new piece of research seems to add yet another layer of complexity to the Tunguska puzzle. So let's approach this methodically and consider what advantages we have now that Kulik did not. The first major advantage is high-resolution satellite imagery. Satellites have mapped the Tunguska region with such incredible precision that we can now see every single tree. The critical question, then, is what have these detailed images shown us? Even after a century, the consequences of the Tunguska explosion are still strikingly visible from space. The vegetation at the epicenter stands in stark contrast to the surrounding taiga. The trees have a different growth pattern, the grass is a distinct color, and the swamps themselves possess an unusual configuration, as if the earth still carries the scar of that cataclysmic event. Although satellites have pinpointed several suspicious, overgrown craters that Leonid Kulik might have overlooked, modern expeditions revealed them to be nothing more than thermokarst lakes, which are common formations resulting from melting permafrost. However, this is where the story gets fascinating, thanks to the emergence of new investigative methods. Researchers now employ ground-penetrating radars that can peer tens of meters beneath the surface, magnetometers sensitive enough to find coin-sized metal objects, and spectrometers that can determine the chemical makeup of the soil with atomic-level precision. These advanced instruments have uncovered something extraordinary in the Tunguska region. Microscopic spheres of melted quartz and magnetite, elevated concentrations of iridium and other rare metals, and distinct anomalies in the crystal structure of local minerals. All of this evidence points to the extreme temperatures and pressures characteristic of a cosmic catastrophe, confirming that something from space did indeed explode there. To understand what that object could have been, we now rely on powerful computer simulations that can model countless scenarios. These models test asteroids of every conceivable size and composition, comets of varying densities, and a full range of entry angles and velocities into the atmosphere. The results are telling. To account for all the observed phenomena, an incredibly precise set of circumstances is required. The object needed to be a specific size, have a particular composition, enter the atmosphere at a very distinct angle, and detonate at an exact altitude. Don't you find that to be a remarkable number of coincidences for a random cosmic event? It almost seems as if every parameter was deliberately chosen to maximize the destructive effect, while leaving behind the fewest possible clues. Modern research has also uncovered a particularly strange anomaly in the rings of trees that survived the blast. In the year of the disaster, these trees experienced a sudden and dramatic spike in growth that continued for several years, almost as if the explosion itself had somehow fertilized the forest. Scientists first theorized that low-dose radiation, which can stimulate growth, was responsible, but they couldn't find evidence of it in the required amounts. Another idea was that the blast had stripped away the topsoil, exposing a more fertile layer beneath, but soil analysis debunked that as well. The mystery endures. What force from the Tunguska event, an electromagnetic pulse, a shift in the planet's magnetic field, or some yet unknown physical effect, could have influenced the vegetation in such a profound way? More recently, Russian scientists have put forward a new hypothesis. Perhaps the Tunguska object wasn't a single solid body, but a rubble pile asteroid, a cluster of fragments bound together and flying in a tight formation. If such an object entered the atmosphere, it wouldn't create a single massive blast, but rather a series of smaller explosions. This theory elegantly explains the conflicting witness accounts, where some people reported seeing one fireball, while others saw several, and some heard a single explosion, while others heard a succession of them. This kind of phenomenon, with multiple detonations at different altitudes and a complex interplay of shock waves, aligns perfectly with what the evidence at Tunguska suggests. Even this compelling rubble pile theory, however, fails to address the most significant problem. Where are the fragments? Even if the asteroid disintegrated entirely in the air, at least some small pieces should have survived to reach the ground, yet not a single one has ever been found. This has led to the possibility that we have simply been searching in the wrong areas. While most expeditions have concentrated on the epicenter of the explosion, it's conceivable that the debris was scattered much more widely, potentially over hundreds of kilometers from the primary impact zone. In response, today's cosmic detectives are adopting a much broader approach to the investigation. Instead of focusing solely on the Tunguska region, they are now examining the object's entire flight path through the atmosphere. They're hunting for atmospheric traces, analyzing changes in the ionosphere, and cross-referencing data with other meteor events. This expanded search is yielding results, such as identified anomalies in radio wave propagation on the day of the event, and unusual magnetometer readings from locations thousands of kilometers away. This indirect evidence strongly suggests that the Tunguska event was a far more extensive phenomenon than we initially believed. Ultimately, one of the greatest advancements in modern science is our capacity to replicate these kinds of events in the laboratory. Using high-speed guns to fire microscopic asteroids and powerful lasers to vaporize meteorite samples, researchers can create miniature cosmic explosions. These experiments demonstrate that such catastrophes are incredibly complex, with the same asteroid being able to form a crater, explode mid-air, or burn up completely, depending on a precise combination of factors. Tunguska appears to have fallen into a very narrow and improbable set of parameters, one that unleashes maximum destruction, while leaving behind minimal physical evidence. While the probability of such an event is incredibly low, it is not zero, and it's something that could happen every 1 to 200 years. As we continue our investigation, modern science is inching closer to unraveling this century-old mystery, yet a definitive answer remains just out of reach. Each new discovery seems to introduce a new set of questions, and every new theory, while explaining some facts, leaves others unresolved. Tunguska continues to be an enigma, but the crucial difference now is that we are finally beginning to understand which questions we truly need to ask. Crucially, we understand that events of this nature are bound to repeat, and the next Tunguska-level impact might not happen in a desolate wilderness, but right over a densely populated city. We have to be ready. Consider the morning of February 15, 2013, in Chelyabinsk, which began as an ordinary workday. People were making their way to their jobs, and kids were on their way to school, a scene of complete normalcy. Then, without warning, the sky detonated. An incredibly bright flash, accompanied by a sound louder than anything the locals had ever experienced, was followed moments later by a powerful shock wave that blew out windows, set off countless car alarms, and injured hundreds with shattered glass. Almost immediately, the internet was flooded with thousands of videos from smartphones, security cameras, and dashcams, allowing the entire world to view a cosmic disaster as it unfolded. The Chelyabinsk meteor thus became the first major celestial event of the digital era, and remarkably, its characteristics were so similar to the Tunguska event that scientists instantly identified it as a contemporary, if less powerful version. A space rock measuring about 20 meters across entered our atmosphere at a speed of 18 kilometers per second, exploding at an altitude of approximately 23 kilometers with a force of 500 kilotons. 30 times weaker than Tunguska, yet still tremendously powerful. Most significantly, we were able to recover fragments from the Chelyabinsk meteor, with hundreds of kilograms of extraterrestrial rock found scattered throughout the region's fields and forests. This provided scientists with an unparalleled chance to examine the material composition of an object that had disintegrated in the atmosphere, just as the Tunguska body had. The analysis revealed that the Chelyabinsk meteorite was a common stony asteroid, categorized as an LL5 chondrite. It was nothing exotic or unusual, just a typical cosmic boulder among millions in the asteroid belt. Yet this ordinary rock became a weapon of mass destruction upon its atmospheric entry. The shockwave from the explosion caused damage to more than 7,000 buildings in Chelyabinsk and resulted in injuries to over 1,000 individuals. The financial toll ran into the hundreds of millions of rubles, and all of this was caused by a relatively small asteroid. The object responsible for the Tunguska event was immensely larger, many dozens of times over. Had it detonated over a major city like Moscow or St. Petersburg instead of the remote taiga, the outcome would have been catastrophic beyond imagination. The incident at Chelyabinsk served as a stark confirmation that the danger from space is very real. This is not the realm of science fiction or Hollywood blockbusters, but an actual, present threat that humanity contends with regularly. While we are often fortunate that these asteroids impact oceans or uninhabited lands, our luck will not hold out indefinitely. The statistics are unforgiving. An object the size of the Chelyabinsk meteor strikes our planet every few decades. A Tunguska-sized impact occurs every few centuries. And an event on the scale of the dinosaur-killing asteroid happens every few million years. The scientific community now recognizes that action is imperative. We can no longer afford to passively wait for the next celestial kamikaze to target a major urban center. We require a sophisticated early warning system, comprehensive evacuation strategies, and, ideally, the technology to deflect dangerous asteroids. Over the last 2 decades, several other incidents resembling the Chelyabinsk and Tunguska events have been documented. For instance, in 2008, an asteroid exploded above Sudan, which was the first time such an impact was ever predicted beforehand. Then, in 2019, an explosion registering several kilotons occurred over the Bering Sea, with each new event supplying scientists with more data on asteroid behavior in our atmosphere. It turns out that this process is far more intricate than we had previously assumed. These objects can detonate multiple times, fragment into smaller pieces, and even alter their course. Our ability to predict an asteroid's behavior remains quite poor. Even when we have data on an object's size, mass, makeup, and trajectory, we are unable to say with certainty whether it will hit the ground or explode in the air, nor can we accurately predict the altitude or force of such a detonation. The number of variables is simply too great, from the angle of entry and rotational speed to its internal structure and density, where even a minor change in one parameter can produce a dramatically different result. Tunguska's greatest lesson was that cosmic dangers don't always appear in the ways we anticipate. We were mentally prepared for a direct impact, envisioning a crater, massive tsunamis, and climate disaster. What we got instead was an airburst that left behind no physical evidence. We were hunting for a tangible cosmic assailant, but it proved to be a phantom that vanished after wreaking havoc. Modern incidents similar to Tunguska reveal that these events happen much more often than we realized, with most going unnoticed over oceans, deserts, and polar ice caps. But every now and then an asteroid finds its mark, reminding us of just how fragile our civilization truly is. The most unsettling part is that we can currently detect only a tiny fraction of all potentially hazardous objects. Astronomers believe we have located less than half of the asteroids larger than 1 kilometer. When it comes to objects the size of those that caused the Tunguska or Chelyabinsk events, we've identified merely a few % of the total population. This implies that thousands of potential Tunguska-sized threats are journeying through space completely unknown to us, any of which could be nudged onto a direct course for Earth by Jupiter's gravity, a collision, or even the solar wind. This is precisely why investigating Tunguska remains so vital for modern science. It is far more than a historical puzzle. It is a fundamental textbook on cosmic safety and a manual for surviving in a perilous universe. The better we grasp what transpired in the Siberian taiga over 100 years ago, the more effectively we can prepare for the threats of the future. These dangers are concrete, and they become more urgent with each passing year, because humanity is no longer dispersed in small towns and villages. We now reside in vast megacities, where millions are concentrated in small geographic areas. If the next Tunguska were to strike such a location, the consequences are something we should strive to prevent, rather than contemplate. Therefore, we must take decisive action by searching, studying, and preparing, all while hoping that we will be ready to confront the next cosmic threat with all the tools at our disposal when the time comes. The good news is that humanity is no longer defenseless against these celestial dangers. The bad news, however, is that these threats are far more numerous than we ever understood. Let's begin on an optimistic note with the narrative of today's asteroid hunters. Picture a building without windows, set deep in the Arizona desert. A lone figure sits before a computer monitor that reveals a star-filled sky, a canvas of thousands of brilliant dots. While the vast majority of these are fixed, distant stars, a few of them drift almost imperceptibly. A red reticle centers on one of these wandering points, marking a potential discovery. This is the work of programs like NEAR, which stands for Near-Earth Asteroid Research, a system dedicated to identifying asteroids that could pose a danger to us. You can think of these dedicated individuals as cosmic sentinels, working non-stop to scan the heavens for objects on a collision course with Earth. Each night, their efforts uncover dozens of new asteroids, most of which are benign and will sail harmlessly through the void. However, on rare occasions, the system issues an alert. When the calculated trajectory of a newly found object veers uncomfortably close to, or even intersects with, Earth's orbital path, a global network of observers is activated. Telescopes across the planet pivot in unison toward this new point of interest, initiating a meticulous investigation into the potential threat. This coordinated effort showcases humanity's proactive defense against celestial dangers. Over the last 2 decades, these surveillance systems have identified more than 20,000 asteroids whose orbits bring them into Earth's neighborhood. Imagine that. 20,000 cosmic projectiles hurtling through space near our planet. This number grows annually, with new discoveries appearing relentlessly. Except these findings are not benign, but potentially catastrophic. The most significant and menacing of these objects are assigned names and placed under perpetual observation. Consider the asteroid known as Apophis. Spanning 300 meters in diameter and weighing 20 million tons, it is a formidable celestial body. In the year 2029, it is projected to pass just 30,000 kilometers from Earth, which is an exceptionally close shave in cosmic terms. Early projections hinted at a slight possibility of an impact, which triggered widespread media alarm, urgent consultations at NASA, and the rapid drafting of emergency protocols. Fortunately, subsequent analysis refined its path, confirming that Apophis will miss us, for now. However, its return is anticipated in the year 2068, and the outcome of that encounter remains to be seen. Even more massive asteroids are lurking in the darkness, such as Bennu, which measures half a kilometer across. The probability of Bennu striking Earth before the year 2200 is 1 in 2700. While those odds might seem reassuringly low, you must appreciate the stakes. An impact from such an object possesses the power to completely obliterate human civilization. It is this catastrophic potential that motivates asteroid hunters to maintain their ceaseless watch. The array of detection systems continues to expand, including projects like LAR, NATE, Spacewatch, and the Catalina Sky Survey, each diligently monitoring its assigned celestial sector for new hazards. Simultaneously, satellites keep a close watch on our planet's atmosphere, logging the flashes of asteroids that explode upon entry, objects we never saw coming. What this surveillance has revealed is staggering. There are approximately 1 million near-Earth asteroids comparable in size to the one that caused the Tunguska event. We face 1 million potential Tunguskas, yet we have managed to locate only a small percentage of them, leaving the vast majority hidden from view. Their elusiveness stems from a simple fact. Asteroids generate no light of their own, merely reflecting the sun's rays very faintly. A dark, Tunguska-sized object becomes detectable only when it ventures within a few million kilometers of us. Traveling at speeds of tens of kilometers per second, this leaves an alarmingly brief window of just a few days for any kind of response. Nevertheless, our technology is constantly improving. New generations of telescopes offer greater sensitivity, while space-based observatories operate free from the distorting effects of Earth's atmosphere. Furthermore, artificial intelligence is being trained to automatically sift through millions of stars to pinpoint asteroids. A significant milestone was recently achieved with the DART mission, humanity's first ever attempt to actively change an asteroid's course. In this historic test, a small probe intentionally collided with the asteroid Dimorphos, and the mission was a success. The asteroid's orbit was altered by several minutes, a minor adjustment that nonetheless provided definitive proof that we can indeed deflect these cosmic threats. Of course, at only 160 meters in diameter, Dimorphos was relatively small. This raises the question of how to handle a Tunguska-sized impactor, or an even more terrifying kilometer-wide behemoth. A single kinetic impactor would prove insufficient against such massive objects, demanding far more powerful strategies. One concept, which may sound like it's straight from a blockbuster film, involves a nuclear detonation near the asteroid, a solution that physicists are genuinely exploring. Models indicate that a thermonuclear blast, detonated several kilometers from an asteroid's surface, could use its shockwave to alter the object's path, carefully nudging it away without shattering it into a deadly debris field. Alternatively, there is the gravity tractor, a method involving a spacecraft that would fly in formation with an asteroid for many years. The vehicle's subtle gravitational influence would gradually tug the asteroid onto a new, safer trajectory. This approach is slow but exceptionally reliable, though its major drawback is the necessity of deploying it decades ahead of a predicted collision. Another proposal is the solar sail, where a huge, reflective mirror attached to the asteroid's surface would use the pressure from sunlight to slowly push it off course. Perhaps the most straightforward idea is to simply paint the asteroid, either white to increase its reflectivity or black to enhance heat absorption. This change in its surface temperature would affect the pressure exerted by solar radiation, incrementally shifting its orbit over time. While these concepts might seem like science fiction, they have all been validated through computer simulations, and some principles have even been tested in space. Technically, diverting an asteroid the size of the Tunguska object is well within our capabilities. The primary obstacles are early detection and sufficient time for preparation. But what if an asteroid is discovered with only days or weeks to spare before it hits? In such a dire scenario, our only remaining recourse is evacuation. Early warning systems are already in place for this exact situation. As soon as a potentially hazardous object is confirmed, the data is immediately sent to specialized command centers. There, its trajectory is precisely calculated to determine the time, location, and scale of the potential impact zone, allowing authorities to activate emergency plans and issue warnings to residents in the affected regions through every available communication channel. When a celestial threat is identified, populations are evacuated from the danger zone, moved to secure locations, and supplied with all necessary provisions. While we have yet to conduct a full-scale evacuation of this kind, the system is in place. The Chelyabinsk meteorite, for instance, was only spotted after its explosion. And other predicted small asteroids have harmlessly impacted deserts or oceans. Nevertheless, this global defense network is active and continually being refined, because it is widely understood that a significant impact on Earth is not a matter of if, but when. And our readiness is paramount. The Tunguska event served as a stark reminder that even a relatively small cosmic body can unleash devastation on a colossal scale. Modern research confirms that space is filled with such objects, far more than was previously imagined. Every day, asteroid hunters pinpoint new potential threats, and with each discovery, humanity becomes slightly better shielded from cosmic disasters. We are slowly but surely learning to navigate our place in a perilous universe, and all that's left is to master our panic when the next Tunguska inevitably arrives. Because it certainly will. Have you ever contemplated the butterfly effect? It's the concept that a minor action, like a butterfly flapping its wings in Brazil, could trigger a tornado in Texas. Though it sounds like an exaggeration, it is a genuine physical principle where the smallest disturbance in one part of a system can lead to massive consequences elsewhere. In a very real sense, the Tunguska explosion acted as that butterfly for all of human civilization, setting in motion a chain of events that reshaped our future. Just consider for a moment what might have happened if nothing had detonated over the Siberian taiga on June 30th, 1908. The world would have likely carried on, oblivious to the dangers lurking in space. Astronomers would have continued observing distant stars, but without the impetus to spend billions searching for near-Earth asteroids, and space exploration would have evolved along a completely different trajectory. However, because the event did happen, an obsessive researcher named Leonid Kulik dedicated a large portion of his life to unraveling the Tunguska mystery. His expeditions were far from fruitless. They established the very foundations of Russian meteoritics. The techniques he pioneered for locating and analyzing meteorites are still employed by scientists around the globe. Without Tunguska, there would have been no Kulik the scientist, no academic school he founded, no students to carry on his work, and none of their subsequent discoveries. Kulik's students proceeded to identify dozens of meteorite craters, assemble unparalleled collections of extraterrestrial materials, and formulate new theories on the formation of our solar system. The Tunguska event also gave rise to an entirely new scientific discipline, the study of astrobleams, or cosmic catastrophes. Before 1908, no one seriously considered that meteorite impacts could be so extraordinarily destructive. The prevailing attitude was that a fallen rock simply made a hole in the ground. But Tunguska proved that these objects can explode with megatons force, leveling entire forests, and profoundly affecting the climate and biosphere. This event forced humanity to confront a terrifying new reality. We are living in a cosmic shooting gallery where an errant projectile from space could strike at any time. This profound realization fundamentally altered our approach to space exploration. While astronomers once studied the heavens out of pure intellectual curiosity, they now had a tangible and urgent mission: to identify potential cosmic killers before they could find us. The asteroid detection programs active today, such as NEAT and Spacewatch, are the direct scientific descendants of the research sparked by Tunguska. The connection to the atomic bomb may seem distant at first, but it is undeniably there. When physicists witnessed the first nuclear detonation over Hiroshima, many were immediately reminded of the Tunguska event, noting the similar effects and patterns of destruction. It became clear that nature had long held the secret to releasing immense energy. In turn, studying nuclear explosions helped scientists decipher the mechanics of the Tunguska catastrophe. And understanding Tunguska provided insights into how shockwaves propagate under real-world conditions. Knowledge later applied to missile defense systems and asteroid defense strategies. Even the field of computer modeling owes a partial debt to Tunguska. The earliest attempts to simulate an asteroid's flight path and the characteristics of its explosion on a computer were undertaken specifically to solve the Siberian puzzle. These pioneering methods were subsequently adapted for a vast range of applications, from forecasting the weather to engineering automobiles. As for the space program, while humans would have ventured into orbit regardless, our perception of space as a hazardous environment filled with debris was decisively shaped by the lessons of Tunguska. Perhaps most surprisingly, the Tunguska event has deeply influenced popular culture. Disaster films depicting asteroid impacts, novels about extraterrestrial threats, and video games centered on defending our planet all draw their origins from the narrative of that mysterious Siberian explosion. Hollywood blockbusters like Armageddon, Deep Impact, and Melancholia are all, in some way, heirs to the Tunguska legacy, illustrating what could happen if such an object were to strike a populated city instead of a remote wilderness. This single event became a powerful symbol of the unknown, fueling endless speculation and inspiring countless works of science fiction about everything from crashed alien ships to time machines and parallel universes. Yet, the most significant impact of Tunguska was psychological. For the first time, humanity was forced to recognize its own fragility. We had grown comfortable with the idea of Earth as our secure home, a fortress protecting us from the cold vacuum of space. Tunguska revealed that our fortress was not nearly as impregnable as we had believed, a shock that gave birth to the entire field of global risk studies. It was only after events like Tunguska that scientists began to give serious consideration to the various threats capable of ending human civilization, from asteroids and supervolcanoes to gamma-ray bursts and climate change. This growing awareness of our planet's vulnerability helped fuel the environmental movement, which is built on a similar understanding. The Tunguska impact was a stark demonstration that our entire world could be altered in a single, ill-fated moment, reminding us that by damaging our own environment, we may not last long enough for the planet to recover on its own. The event also taught us a crucial lesson about international cooperation. as cosmic dangers completely disregard national borders. An asteroid impact in Russia, for instance, could easily set off climatic shifts in America, making planetary defense a shared responsibility. Consequently, this has become one of the rare fields where political rivalries are put aside, leading to remarkable partnerships like NASA working with Roscosmos, the European Space Agency sharing information with Chinese researchers, and Japanese astronomers collaborating with their Indian counterparts. There is a universal acknowledgement that when confronted by a threat from space, all of humanity stands together as one. Our approach to education has also been transformed. It is now common for school textbooks to feature sections on asteroids and comets, teaching children from a young age that the cosmos is more than just stunning telescopic pictures. It is a source of tangible threats. This shift frames science not as theoretical knowledge, but as an essential instrument for our survival. Tunguska has become emblematic of this dangerous cosmos, consistently referenced in space museums, featured in planetarium films about asteroid hazards, and used as the opening story for popular astronomy talks. A whole suite of modern technologies owes its existence to the century of investigation following the Tunguska incident. This includes advanced systems for monitoring near-Earth space, automated programs for detecting asteroids, and sophisticated methods for calculating their trajectories. Had it not been for this event, humanity would have addressed the challenge of cosmic security much later, and with far less readiness. Without it, we would have been far more vulnerable. Just try to picture an alternate timeline where the Tunguska event never occurred. Civilization might have evolved without any awareness of dangers from above, blissfully ignorant until an asteroid comparable to the one that wiped out the dinosaurs suddenly hit a major city, with no warning, no plan, and no chance for evacuation. Instead, we were given a crucial head start. A century to study cosmic disasters, comprehend their effects, and develop technologies for detection and defense. This is the true inheritance of Tunguska, an explosion that happened in precisely the right way. Had the object landed in the ocean, its impact would have gone unnoticed. Had it obliterated a city, the human tragedy would have eclipsed any scientific inquiry. But because it struck the remote taiga, creating a massive disturbance and a lasting puzzle without causing human casualties, it became the ideal learning opportunity for our species. You can see this as a perfect illustration of the butterfly effect. A single blast in the Siberian wilds set in motion a series of changes that, while gradual and often unseen, have fundamentally altered the trajectory of human civilization and continue to influence our path. And this leads to a fascinating paradox. The deeper our investigation into Tunguska goes, the more it seems a final, all-encompassing answer may be forever out of reach. More than 115 years after the sky ignited over the Siberian taiga, after countless expeditions, studies, and hypotheses have produced mountains of data, we find ourselves knowing nearly everything and nothing at all. We have pinpointed the exact moment, June 30th, 1908 at 7:14 in the morning, and the location, over the Podkamennaya Tunguska River. We have calculated its force at 10 to 15 megatons, its altitude at 8 kilometers, and the devastation it caused, covering 2,000 square kilometers. Yet the single most critical detail remains a mystery. What was it that actually detonated? Consider the leading explanations. The asteroid hypothesis is scientifically plausible and accounts for many of the observed phenomena, yet it fails to address why no significant fragments have ever been discovered. why the blast pattern was so perfectly symmetrical, or why the chemical signatures in the soil do not align with typical meteorites. Similarly, the cometary theory is attractive because it neatly explains the absence of a crater and the blast's symmetry, but it introduces its own problems, such as the comet's mysterious origin in late June, the fact that no astronomers of the era observed it, and how such a fragile, icy body could produce such a tremendously powerful explosion. More outlandish theories involving UFOs, antimatter, or even miniature black holes can account for the truly bizarre aspects of the event. But they demand leaps of faith based on scant evidence that contemporary science simply cannot endorse. It is at this point that you might start to realize that a solution, in the traditional sense, may not even exist for the Tunguska mystery. It is possible we are imposing our desire for a simple answer onto a profoundly complex event, forgetting that the universe is under no obligation to be straightforward. Modern physics itself is built upon paradoxes and uncertainties that challenge our everyday intuition. You have quantum mechanics, which allows a particle to be in multiple locations simultaneously, and relativity, where the passage of time is not constant but depends on your velocity. Then there is Heisenberg's uncertainty principle, which states that you can never perfectly know a particle's position and momentum at the same time. What if the Tunguska event is a similar kind of paradox, a phenomenon that defies explanation by any one simple theory? Perhaps the truth lies in a unique convergence of circumstances, an asteroid with an unusual chemical makeup, hitting the atmosphere at a precise angle and speed, all under a rare set of atmospheric conditions. You know, it is worth remembering the scientific principle known as Occam's razor, which suggests that the most straightforward explanation is often the right one. But whether that applies to a mystery as deep as this one remains an open question. However, we must also consider the counter-principle known as Hitchens's razor, which posits that any extraordinary claim demands equally extraordinary proof. The Tunguska event undoubtedly falls into this extraordinary category, which perhaps leads to the most accurate answer we have. We may not know precisely what it was, but we have a firm grasp on what it could have been. We possess a roster of credible explanations, a comprehension of the physics at play, and our capacity to foresee and defend against similar occurrences is constantly improving. But does humanity truly need an absolute, final answer? Or is functional knowledge sufficient for our needs? A doctor doesn't require a complete understanding of aspirin's molecular mechanisms to effectively alleviate a headache, just as an engineer can construct a stable bridge without delving into quantum mechanics. In the same way, perhaps knowing the exact composition of the Tunguska object isn't necessary for us to shield ourselves from comparable threats in the future. Ultimately, the Tunguska incident has already served its purpose. It compelled our species to take cosmic dangers seriously, fueling the growth of entire fields of science, and teaching us the vital importance of searching for threats, modeling their behavior, and planning for the worst. Is that not a significant enough contribution? Its greatest value might just lie in its enduring mystery, as it is an event that keeps scientists vigilant, pushing them to invent new research techniques and formulate audacious hypotheses. If this puzzle had been solved within the first few years, our collective interest in the subject might have dwindled. As things stand, the mystery remains vibrant and continues to evolve, acting as a powerful catalyst for progress. Science has a remarkable quality in that it does not depend on final answers. In fact, every discovery tends to generate a new set of questions, Every solution unveils fresh enigmas in an unending cycle of discovery, where the journey itself holds more significance than the destination. In this way, Tunguska has become an icon of this scientific process. It represents a mystery that teaches us to pose better questions, a problem that refines our methods of investigation, and a secret that makes the pursuit of knowledge thrilling. It is conceivable that a century from now scientists will uncover the definitive solution. They might develop a time machine to witness the 1908 explosion firsthand, or create an artificial intelligence capable of analyzing every scenario to identify the correct one. Then again, maybe they won't, and that is perfectly acceptable. Science is as much about the questions we ask as it is about the answers we find. The Tunguska event posed one of the most critical questions to humanity. Are we prepared to confront the unknown? Thus far, our response is encouraging. We are making preparations, slowly and with occasional missteps, but the effort is underway. This is the primary legacy of that enigmatic explosion in the Siberian taiga. Not a specific piece of knowledge, but the drive to know. Not a final resolution, but the capacity to search. Now, my friend, let's shift our focus to the world we inhabit today, because Tunguska is not some unique, isolated catastrophe from the past. It serves as a stark reminder of the everyday reality of our existence. You and I are living in a game of cosmic roulette, where the ball can land on the wrong number at any given moment. Picture a standard roulette wheel with its 37 slots and the tense excitement of the players. But now imagine the stakes are not monetary, but the very survival of human civilization. This high-stakes game runs 24 hours a day, without pause for weekends or holidays, every second of every day. That is an accurate depiction of our existence when viewed through the lens of cosmic security. Earth hurtles through space like a moving target in a celestial shooting gallery, surrounded by millions of potential projectiles like asteroids, comets, and other space debris. While most of them drift by without incident, every so often the ball lands in the wrong slot, resulting in an event like Tunguska, Chelyabinsk, or something far more devastating. The most terrifying aspect of this situation is that we don't even know the total number of slots on this cosmic roulette wheel. Astronomers have managed to identify only a tiny fraction of the objects that could potentially pose a hazard. At best, this amounts to about 10% of the total. The remaining 90% are lurking out there in the darkness, completely invisible and unaccounted for. Each day, approximately 100 tons of cosmic material, equivalent to the weight of a small airplane, enters our atmosphere, though most of it incinerates harmlessly as meteors. But statistics paint a relentless picture of what can penetrate deeper. Objects the size of a car impact our planet roughly once a year, house-sized objects about once per decade, and Tunguska-scale events about once a century. An impact comparable to the one that eradicated the dinosaurs occurs on a scale of tens of millions of years. While it may feel as though the next global catastrophe is a distant prospect, statistics deal in averages, and reality can deviate sharply from the mean. A civilization-ending asteroid could arrive tomorrow, in 1,000,000 years, or several could appear simultaneously, as nature is not bound by our statistical models. Then you have the comets, which introduce a profound level of unpredictability. They originate in the remote Oort cloud at the very edge of our solar system, and their journey toward the sun can take millions of years. We typically only become aware of a comet when it is already quite close, far too close for us to take any effective action. Imagine an icy mountain the size of Everest that has been hurtling directly toward us for 1,000,000 years, completely undetected because it is too distant and dark to be seen. We would only learn of its existence once it entered the inner solar system and began to glow from the sun's heat. Compounding this threat are dark comets, which are as black as coal and reflect almost no sunlight, making them virtually impossible to spot until the final moments. An object like this could sneak up on us, and asteroids approaching from the direction of the sun are entirely invisible to our telescopes. The sun's glare blinds our instruments, which is exactly how the Chelyabinsk meteorite arrived unseen, hidden in the solar rays. Space is not an empty void. It's a dynamic arena where bodies like Jupiter can use their immense gravity to alter an asteroid's path at any time. A comet's trajectory can be altered by the solar wind, and a collision between two objects can unleash a shower of debris in every direction. Yet, these are not our only concerns, as even greater threats loom. Consider gamma-ray bursts, which are stellar explosions powerful enough to sterilize half a galaxy, or supernovae that could obliterate Earth's ozone layer. Imagine rogue black holes capable of consuming our entire solar system. Moreover, some of the most significant dangers are of our own making, from the millions of fragments of space debris that already endanger astronauts, to the ultimate outcomes of nuclear war, runaway artificial intelligence, or nanotechnology gone awry. What's truly fascinating, however, is that you and I have learned to coexist with these existential risks. We don't spend our days consumed by anxiety over asteroid impacts or distant cosmic explosions. Instead, humanity has developed a sophisticated approach to managing these dangers by studying them, assessing probabilities, and coordinating international efforts to create protective technologies. We have learned not just to live with uncertainty, but to actively prepare for it, a crucial lesson that began with the Tunguska event. That incident was our first real education in this new school of cosmic survival. It demonstrated that these threats are not theoretical, but tangible, and that our response must be proactive, not passive. As a result, we now have established protocols for when a dangerous asteroid is identified, including technologies designed to divert its path and systems for evacuating populations. We've established a global framework for cooperation during such emergencies, ensuring we face these challenges together. Yes, our existence still feels like a cosmic game of chance, and the dangers have certainly not vanished. The difference now is that we are no longer blind participants simply hoping for good fortune. We have become players who understand the rules, employ a clear strategy, and recognize that this is a game without an end. The price of living in a dynamic universe is the constant presence of these threats. But this reality is not a reason for despair. It is a call for mobilization. Each successive generation will be confronted with its own set of cosmic challenges. Our responsibility is to pass down the knowledge, technology, and experience we have accumulated, teaching them not to fear space, but to explore it, and not to hide from threats, but to prepare for them. The Tunguska event gave us a 100-year head start to get ready for the next major cosmic event. While we have used that time effectively, the cosmic roulette continues to spin, and there is still a vast amount of work to be done before the ball lands on our number again. When I reflect on this story, it's clear to me that Tunguska offered humanity something far more valuable than scientific discoveries or defense systems. It gifted us a completely new framework for thinking about our place in the universe. Before 1908, space appeared distant, serene, and fundamentally safe. The stars were just beautiful lights, and meteorites were little more than museum curiosities. That single event proved that space is, in fact, our immediate neighbor, one that can arrive unannounced with the force of an atomic bomb, transforming our world into a target in a giant cosmic shooting gallery. Faced with this new reality, humanity could have recoiled in fear, but instead, we chose curiosity. We didn't retreat into shelters. We initiated studies and began searching for ways to protect ourselves. Tunguska became a powerful catalyst for progress, forcing us to take science more seriously and to explore space not just out of a sense of wonder, but out of sheer necessity. This shift changed everything, turning research into a vital need and highlighting the triviality of political disputes when faced with a common cosmic threat. Ultimately, the event taught us humility. It shattered the illusion that we are the masters of our planet and revealed us to be just one species on a small world, adrift among billions of potentially lethal objects. This is a sobering thought, but it is also liberating. When you grasp the true scale of the universe, our terrestrial conflicts over borders seem utterly insignificant. Tunguska provided us with a cosmic perspective, a view from which it is perfectly clear that we are not enemies, but a unified crew on a spaceship called Earth. This vessel journeys through the perilous waters of the cosmos. The Tunguska event showcased the elegance of science, demonstrating how, from scattered evidence, indirect clues, and daring hypotheses, we can reconstruct the image of an event that happened a century ago. It revealed the scientific method in action, not as a rigid dogma, but as a creative force. It showed how scientists are unafraid to acknowledge their errors and revise their theories, making the century-long study of this mystery a powerful lesson in intellectual honesty. Researchers did not try to bend the facts to fit their preferred narratives. Instead, they admitted when the data was insufficient. They persisted in their search even when the trail seemed to have gone cold. This dedication illustrates that science is not a collection of established answers, but a relentless process of pursuing the truth. And this pursuit is far from over. As new information about Tunguska surfaces each year, new theories are put forth each decade, and every new generation of scientists examines the old enigma with a fresh perspective, uncovering something novel within it. Perhaps in another 100 years, the mystery will be conclusively solved, or maybe it will give rise to new questions we cannot currently conceive. Ultimately, that distinction is not what matters. The crucial part is that the quest continues, that humanity's curiosity about the universe remains undiminished, and that we do not shy away from asking the most challenging questions. Tunguska also imparted another vital lesson: the significance of uncertainty in a world where the internet offers ready-made answers and artificial intelligence tackles ever more complex problems. In an age where science can seem increasingly predictable, Tunguska stands as an island of genuine mystery. And this is a wonderful thing, because enigmas compel us to grow. Uncertainty fuels creativity, and secrets are what make life truly engaging. A world without them would be a profoundly dull place. Crucially, the event transformed our very understanding of what is possible. Before it, human thought was confined to terrestrial scales. Afterward, it expanded to cosmic ones. Before Tunguska, catastrophes were measured by ruined cities. After it, by incinerated forests the size of nations. Tunguska broadened our imagination, proving that reality can be more incredible than any work of fiction, and that nature is more inventive than any writer. It showed us that the universe is filled with surprises we have yet to even dream of. And therein may lie the true value of the Tunguska enigma, not in any specific scientific outcome or technological breakthrough, but in the simple fact that it made us wiser. It taught us to coexist with uncertainty, to brace for the unexpected, and to face the unknown without fear. 115 years ago, something detonated over the Siberian taiga. While we still don't know precisely what it was, we understand that this event changed us profoundly. It made humanity more inquisitive, more resilient, and more unified against cosmic threats. And this, perhaps, is the real solution to the mystery, not in what descended from the heavens, but in what rose from the earth. The answer lies not in the nature of the celestial object, but in the character of the human response to that challenge. Tunguska held up a mirror to us, and we were pleased with what we saw. A civilization that does not surrender to mysteries, but instead converts threats into opportunities. We saw a species that learns from its mistakes, embraces the future, and is prepared to meet the universe's challenges with dignity. Tunguska was an examination of our maturity and our readiness to become a spacefaring people. And I believe we passed. It may not have been with top honors, but it was a solid performance. And, most importantly, we learned that these tests will continue, and we are ready for them. The explosion that no one witnessed transformed everyone who learned of it. The mystery that no one solved educated all who investigated it. The catastrophe of the past has equipped us for the trials of the future. This might be the true magic of Tunguska. It is found not in what it hides, but in what it reveals. Not in what it raised, but in what it built. Not in what it took away, but in what it gave. It is a mystery that has reshaped us, and continues to do so with every new study, every fresh hypothesis, and every different angle on this old riddle. So thank you, Tunguska, for the lesson, the challenge, and the reminder that we inhabit a magnificent and hazardous universe, a reality that should inspire awe, not fear. The mystery lives on, and that is a truly wonderful thing.